Hi, welcome to today's webinar for ADAPT PTRC. My name is Spencer Lee. I'll be conducting the webinar today. And we're also going to record the webinar for those who are unable to participate. If you have colleagues or others that wish to view the recording, all of our webinars are placed on our YouTube channel, which is youtube.com/adaptsupport. And you can go to the ADAPT Webinars playlist there where we save and all of the recordings for playback. So if you have questions related to this particular webinar or for Builder or excuse me, PTRC version 2017, you can always contact us at support@adaptsoft.com. So today's webinar will cover the features that are included in version 2017 of the PTRC release. The release officially occurred a couple of weeks ago, and just for a matter of bookkeeping, we are currently collecting licensing information for those of you that have active maintenance agreements with ADAPT. You are eligible to update to this particular version. We have had one issue where we have to update and upgrade our licensing files within the program, so that should not prohibit anyone from getting the software. That's been done, and for those of you who want to get upgraded immediately, just please contact us again at support@adaptsoft.com or licensing@adaptsoft.com. And also to note, our typical release schedule is such that when we release a software, we always stagger the release in terms of communication with clients. We contact the primary contact within a company, and we begin with platinum level clients and then work our way through gold and maintenance only. So if you are on maintenance only or gold and you wish to upgrade again, just contact us and we'd be happy to get you upgraded. So we're going to go ahead and start. If you have any questions, please feel free to enter the question. There's a question box on your GoToWebinar panel, and I'll be happy to answer questions relating to the new version. If you have more in-depth questions that might be related to a specific project or a specific file, we just ask that you send those to support@adaptsoft.com, or you can call us also at 650-306-2410. That's the main support line. So we'll go ahead and get started. We're going to work from these PTRC release notes. Now keep in mind there are additional improvements than what we're going to cover today, and those improvements are typically minor bug fixes and other enhancements that are found in the log file of the software. So if you were to install the software and you navigate into the program files directory for the program, you'll be able to find the log file which itemizes each of the different improvements, including those that we're going to go through today. Today's webinar should last roughly 30 minutes to 45 minutes. So we'll go ahead and get started. The first thing we'll show or discuss really is just what's been included in terms of new codes. We've added the Canadian version 2014 code. So if we go into the ADAPT input screen for one-way slab, two-way slab, or beam, you'll see that if you're working in metric SI units, you'll have the ability now to select Canadian or the 2014 or the 2004 code. That's been there previous. And inclusions made for this particular code, the most notable inclusion really is if we go over to the input for cover, so under minimum covers, you'll notice that there's a cover for clear bar cover, and there's a side cover here. And this input is really only applicable to the Canadian 14 version of the program. It's meant for a requirement where the width of the beam gets reduced for one-way shear when the shear force is greater than some multiple of the shear capacity. So if you see this in ACI code, we're not doing anything with it in ACI currently. It is a placeholder for additional improvements we will make for deep beams later down the road for ACI. So that is the most noticeable input change in terms of the Canadian code. The next thing we want to talk about is how the program calculates minimum reinforcement for systems that include two-way slab systems, particularly that include drop panels, drop caps, or transverse beams. So we'll go ahead and open a file to show this. I'll go ahead and navigate to this location. Okay, so we're going to open this model. It's an ACI model, and this is in US units for this particular model. When you select two-way slab, you'll notice that under drop caps, drop panels, and transverse beams, there's some explicit input for being able to model the geometry of those systems. And when two-way slab is selected, when you use conventional reinforcement, you'll note that under the design settings, there's an option now for including or considering the drop panel for the purposes of calculating minimum reinforcement over supports. And this is available for both PT and RC systems. So in previous versions, the program was hard-coded to calculate minimum reinforcement over supports relative to the slab depth. And we have write-ups as to why ADAPT went that route in terms of background and just theory-related information. But multiple clients have asked if we can include this. So if you select this button or this option, the program will use the area of the drop that the section cuts through in calculating the minimum reinforcement. And just to show you an example of this, in this example, the option is selected as being on, and we'll show you the exact same model with the option off, and you'll just see the difference in the reinforcement where this is calculated. So we'll run this file, and while that file is running, I'll go ahead and open up the other file. Okay, so we have the first file. Let's see, we'll go ahead here, and the force here, I'm just going to change to 550. I'll recycle that. And for two-way slabs, the force really doesn't matter in terms of the minimum reinforcement over the supports, but we just want to have the same solution for both to compare. In the other model, I'll go directly to the recycler. So this is the model with the selection. Let's see if we can find that right model. I have two working at the same time here. Okay, so this is the model with the selection turned on, where we would expect more reinforcement over support. I'll go ahead into the builder summary sheet, and under the service 1 or service 2, they both give the same answer in this case. You'll see the rebar over the support is around 3 square inches. If we go to the solution where the selection is turned off, you're going to find that the reinforcement is roughly, I think, 2.1 or 2.2 square inches. So this just allows us to compare what the selection is doing. I'll go back to the same service case. You can see here it's 2.16. So that selection is made. It is also available if you use segmented geometry. So if I go back into the input, and let's say instead of using the explicit input for drop panel, drop cap, transverse beam component input, we'll go ahead and select no, and I'll go to segmented. Notice that just simply goes away. If we go back, you'll notice that this is still there. So whether you do conventional or segmented input, the option is available for both. Okay, the next thing we'll look at is a improvement made for the calculation of self-weight for a system. So if we'll just use the same model. If I go back into the material assignment, so for concrete material, you'll notice right here I have normal weight selected. If I go back one level to the loading, the program automatically calculates the self-weight for whatever concrete assignment you've made. So here it's 150 pounds per cubic foot. It would just be the equivalent for other codes or other unit systems. And this is grayed out, it's inactive. If I go back to the input and I change this to semi-lightweight, you'll notice this changes to 115. So there were some expressions made by users that even if we're using semi-lightweight or maybe lightweight concrete, we still want to assume a higher value for unit weight. The program was automatically changing that, and in this case we've added this switch. If you want to override this calculated value, just select the checkbox or deselect the checkbox, and you can come in here and override the unit weight value. So that is new to the program, that checkbox within the loading input. If you choose to include self-weight, that's available. If you do not choose to include self-weight, then you would directly input the loads here in the input table for the loading. Okay, the next thing we'll look at is also applicable to the Canadian code, and we're going to compare the result for this next option between an ACI model and a Canadian CSA model. I've actually changed the strength factors for the load combination for strength such that they're the same. Both codes are very similar in nature, so we use this as a basis of comparison. In previous versions of the software, when you're selecting CSA 2004, and in this case that was the only case or the only design code available previous to this version, what would happen is when you had a drop panel or a drop cap that didn't meet the ACI restriction of L/60 either side, the program would apply that same restriction to Canadian and ACI codes. So if the drop panel did not extend a distance span over 6 to either side, the program would discount it in terms of checking or calculating flexural reinforcement. It would ignore the drop, and it would only use the slab depth for determining the effective depth of the member. That is not required in the Canadian code. So we changed the Canadian code such that it will always use the effective depth of the drop if you model the drop when calculating the reinforcement. So we'll go ahead and open a model to show this. And the first model I'll open is the ACI control model. So this includes, this is in metric, this includes a drop. You'll see here this is the explicit drop panel geometry. This value for the distance to either side, both in the plane of the slab and also out of plane, is 1,300 millimeters. The requirement is roughly 1,500. So this technically doesn't meet the L/6 requirement set by ACI. And if we go ahead and run this model, we'll compare this to the same model run in the Canadian code, version 2014, and you're going to see there's a pretty big difference in terms of the reinforcement that is output by the program in this case, because the Canadian code is using the effective depth regardless of its plan dimension. So while that's running, I'll open up the CSA model. It's this model here. And I'll go back to my control model. In the control model, you can see we're going to set the force equal to 500 kilonewtons. This is a pretty low force. We're just forcing the program to add non-prestressed reinforcement. In reality, for this design, the post-tensioning took care of the flexural demand, so we have to back off the force to force it to show what we want in this example. So we'll go ahead and set that down to 500 kilonewtons, and we'll recycle. We'll go ahead now and exit out of the recycler. Okay, and if we look at the reinforcement necessary to meet strength 1, strength 1 is 1.2 dead plus 1.6 live, and includes the hyperstatic effect. So we'll look at the reinforcement here, and we can see that the reinforcement over supports is pretty high. It's around 11,000 square millimeters for the control model, the ACI model. Now, if we go to the Canadian model here, and in this case, we're going to set the same force equal to 500 kilonewtons. So that's the same exact force and profile as the previous ACI model with the same level, or let's say factored loads. There may be a difference, a slight difference in the material strength factors, but we're ignoring that for now. That clearly wouldn't make up the difference in how much reinforcement is required between comparing both models. Okay, so the previous model in ACI was around 11,000 because the program is not considering the effective depth of the drop. In this case, the Canadian code is considering the effective depth, and you can see this is roughly 4,100. So it's about 2.5 times less than the required amount in ACI. So that has been changed for version 2017. Just to summarize, for any design made in the Canadian code for a two-way slab, the program always considers the drop panel or drop cap or the transverse beam depth when calculating reinforcement at strength level over supports. The next thing we'll look at is just a graphical improvement, and I'll go ahead and open up an example file for this particular improvement. This applies to any design code, ACI, Canadian, Hong Kong, whatever code you're using, and it's applicable to beams and one-way slabs where we check one-way shear. So in the summary sheet, in the builder sum summary sheet under envelope, or if you go to an individual strength combination, strength 1, 2, 3, or 4, whatever strength combos you have set to be evaluated in the model. If you turn on the summary sheet, you're going to see that under the shear stirrup block, any shear stirrup that where the shear force VU exceeds the concrete shear capacity, not the concrete plus reinforcement, just the concrete capacity, those will be marked red. So you can see along this beam there's several black lines. Each one of these lines is where we have a demand for shear reinforcement. And where you have red, that means that VU has exceeded, let's say, PVC, if we look at it in terms of the ACI code. Where we have black, that means that VU is greater than 1/2 PVC, but it does not exceed PVC. It's within that realm where you need minimum reinforcement. So this is just a graphical indicator where you have that occurrence. And if we look at this block, we can always zoom in. It's hard to see that color here unless we zoom in a bit, but that is shown color coded here in the builder summary sheet. Other improvements made graphically. Anytime we are looking at a stress graph, so this could be in the recycler screen. If I go into the recycler here and I go to graphs, you're going to see that for any stress graph, bottom fiber, top fiber, for sustained, total, or initial, any of the combinations that we check stress for, the program will now report the maximum and minimum stress value along the graph. So you can see these numerical values here that the program is reporting. If we right-click and maximize, those are a little bit easier to see. But this will report max and min for all spans along the graph. That's reported again in Recycler. If we exit Recycler, we go into what's called the shell. And in the shell, there's an option to check stress graphs as well. Those graphs would also show the same thing. So here I go into the graphical results under stresses. Again, top or bottom fiber, the same types of values will appear. And also in builder sum, we look at a service combination and look at the stress graphs here. You can see these graphs do not show it. So it's in shell and recycler only. The combination graphs are simply color coded. They show the allowable in gray with the actual stress green or blue. Green in tension, blue in compression. Okay, for the ACI code, there's a requirement that and it's found in ACI 318 2014 version. It's found in 9613. That's the section reference, where if your minimum reinforcement exceeds that of strength by about 1/3, 1.33 or 4/3, then you only have to reinforce it at a level of 4/3 times strength. So in previous versions of the software, the only time that was really evident, and this is for RC beams, by the way, the only time that was evident was when you looked at the envelope results for the reinforcement. So let me go ahead and switch over to RC mode, and I'll just use the action convert the project to RC, and then I'll go ahead and open the file that we're going to look at. And this is applicable again to beams and one-way slabs, RC beams and one-way slabs, not two-way slabs. So this example is a T-beam, and I'll go back and open that example up. Make sure I have the right model here. Okay, so this model again is an RC beam. We have 3 spans of 28 feet. It's a T-beam. You can see the middle span has only dead load, superimposed dead load plus self-weight. The 2 outer spans include live load. And this seems like strange loading, but the purpose was to show the result. So when we execute this model, now I've calculated the minimum reinforcement based on section 10 of the older ACI codes. Section 9.6 of the new ACI code, section 10 of the older codes. Minimum reinforcement for this beam is roughly, I believe, 1.12 square inches. And let's go ahead and run the model. And that's just based on 0.0035 times the web width times the depth, B sub W times D. Okay, and let's get back over to that model. I'll go into builder sum, and the first thing I'm going to look at is my service. Service 1 is actually blanked out. It's zeros, but it will report the minimum rebar anyway for both service combinations. I'll go to service 2. That combination is just total service. And if we look at this result, we can see that the amount of service rebar we need for the outer spans is 1.12. That's the 0.0035 times B sub W times D. You can see the middle span is actually 0.3, so it's quite a bit lower than 1.12. In older versions of the software, if you were to design this slab, this would show as 1.12, and the envelope would show the reduced value based on the provision that I referred to earlier. So in this version, if that provision kicks in, the service combinations individually will show the reduced value. And let me go over here to strength so we can kind of get a basis for what that is. You can see that the requirement for strength in the outer spans is 3.85 square inches, which is quite a bit higher than service. It's 3 times plus higher than 1.12. So the provision doesn't apply in this case. In the middle span, the requirement for strength is 33% less than that required for service. So in this case, what we're doing is we're taking the 0.23, we're multiplying that by 1.33, which is 0.31, less than 1.12, so that 0.31 controls the minimum reinforcement, and that's what is reported here. It's 0.3, so the result is always now shown in this graphical view for service and also for envelope. Again, to summarize, in previous versions, it was only shown when you went into the envelope of the system. So that has been modified in this version. One other thing that we've done is we've allowed the replication of any report to be produced in Excel. So if we go into the report generator, it can be for any type of system, whether it's RC or PT mode. If we go into report generator, let's say I wanted to produce a report for compact, for input geometry, section properties, steel, and let's say punching shear. And I use this option to create an optional spreadsheet report. If you select that option and you create the report, the program will open both the Excel spreadsheet and it will also create the Word document. So we can't differentiate between the two. In other words, you can't create the Excel report but not the Word document. It will always create both. So you have the ability to create the Word document individually or both reports. This is showing the Word document. If I go and minimize this, open up this Excel sheet, each of those sections blocks in the report document are then an individual sheet inside of this Excel book that's opened, and you can see this is block 2, input geometry 4, 10, 13. So this just helps. This has been a user request for a while, and those that want to do some post-processing of data, this would be helpful. It's probably more helpful if you're using it in conjunction with the detailed reports, because that produces quite a bit more data for each individual design cut along each span. And note also that if you create default reports or you create custom reports based on your selection here, and this is selected, this check or this switch does not get saved as part of the user selected or customized report setting. So you would still have to come here and switch that on if you wanted to apply it to a saved report. Okay, the last thing we're going to show today is hybrid design in the program. Now, in past versions of the program, the user could always go in and set up a model and blank out the tendon A, add tendon B or C, and create a gap between both tendons B and C, let's say maybe for a pore strip. And you could kind of force the program to do a hybrid PT with some section of being RC and then PT. So we consider that a hybrid design. However, in that case, the program would still apply minimum reinforcement to those sections that didn't have any post-tensioning passing through them. So we've done some work on applying the correct reinforcement to sections that are RC, that have no post-tensioning inside of them. So let's open up a test model here, or an example model. This is a 5-span, 2-way system, and what we're wanting to do in this case is we want to add, let's say, a pore strip at some location here. And so we're going to have a tendon that does this, and then it just stops here, and then another tendon that does something like that. This is going to be tendon B, and this is going to be tendon C. Tendon A is always present in our model. So tendon A always goes from start over here to end. So the only way to discount or to avoid tendon A actually being used is just to simply set its force to 0. So that's what we're going to do in this case. If I run the recycler, or let's say execute the model, let me go ahead and delete that. I'll recall the solution. Now when I recall the solution, I'll recycle again to update the result. And under graphs, you can see that, I'll maximize this, we have tendon A, which is shown. That's the red tendon. And then we have tendon B, which is this blue tendon. You can see it stops right here. Tendon C picks up right here and anchors out the right-hand side. Give me one sec here while I'm trying to, okay, we're back in here now. So what you'll notice in the block number 1 of the recycler, tendon A is set to 0. We zero out the force so that no force passes through that location where there's a pore strip. Tendon B is set to 510 kips to meet the requirements between spans 1, 2, 3 and part of span 4, or I should say the support at the left side of span 4. And then tendon C is set to 800 kips on the last span and then partially into the second to last span from the right. The way that these tendons are set up is set in block number 5 here, and in tab 5 we've run tendon B 20%, 3.2 from this support, so it's 20% to the right, and tendon C is 50% to the left of this support here, so this is support number 5. And so we get this gap. This represents our pore strip in the model. And the user can always adjust these. If you press Control, grab that tail and slide it back and forth, you can adjust the anchorage points, or you can enter it here as an input, numerical input on this table over to the right. So one thing to note is when you have this type of a system where you're only using tendon B and C and there's a gap, if I go back to my graphs, you can see the force comes along here at 510 kips and then it just suddenly drops to 0, picks back up to 800. This is where obviously we have no force. That's our pore strip. There's no requirement there, so this actually helps me determine where I might want to place a pore strip because I don't have a required force there. The program would still show you a requirement if you need one to meet allowable stress and so on, but here we don't have that, so that's a good guide to showing us where, again, we might put the pore strip or place that. One thing to watch out for is these checks at the top for pre-compression, balance loading, and stress. Those still apply to sections that are not intersected by tendons. So you can see right here it says PT force minimum is no good, balance loading is no good. If I check my graphs again, I can see that the bottom total stress is completely satisfied. I don't have a stress problem. The total top fiber stress is also satisfied. It's close at this location here and over here, but again, if I maximize that to show that these are right on the dot for the design. So the stresses are okay relative to the allowable stress, but my pre-compression and my balance loading are basically 0 at the pore strip. So right here you can see within span 4 there's a section where I don't have any pre-compression, and that's actually triggering that no good here. However, at that location we don't technically need the pre-compression because it's a pore strip. So we're going to improve that in a next build of version 2017 and be able to flag this only with respect to post-tensioning design sections, not RC. But for now, just be aware of this. And also the balance loading in those sections is 0. So that drops below our input. In this case, the balance loading minimum input was 50%, and that flags that also. But in reality, this design is acceptable. So once we exit out of here, and I go over to, let's say, the builder sum summary sheet. I'll just look at the envelope sheet here. You can see tendons B and C are only those shown. There's our pore strip. There's the anchorage of each of these tendons. And when I look at the envelope of reinforcement, we have our bottom and top reinforcement. We're going to expect a different, let's say, a different calculation with respect to minimum reinforcement for the sections within that zone, which is, in this case, that would be based on just minimum temperature and shrinkage reinforcement, 0.0018 times the gross area of the concrete. And in the previous version, it would have been calculating the reinforcement here from a minimum standpoint based on the stress level. So if the stress level was very high, we had no post-tensioning there counteracting the stress that was being generated by the gravity load. We would get a bunch of rebar in this location just based on the level of stress greater than 2 times the square root of F times C in this zone. So I'll go over here to service, and you can see here we have 3.75 square inches of steel for these section cuts. If I was to go into the reinforcement diagram, I just notice that this is just the same for each one of these sections. That tells me that each one is being calculated for minimum temperature shrinkage. In the previous version, these would not be identical because they would be based on the stress level, and that stress level changes as you move away from the support at a different section cut. So that is how the program now handles hybrid sections within PTRC. So that will conclude some of those features. Again, if you want to investigate into more of the features, you can always go into the program files, and I'll show you where you can navigate here. If we go into the program files on your computer system where the program is installed under the PTRC folder, there's a log file. This is also an attachment where on our download page under the documentation tab. So whenever you receive the download page, all of the documentation is there, including the log file and the release notes. This log file outlines everything that was fixed or improved in this version, as well as older versions. This is just a historical list of everything that's been worked on. But if there are any questions now, I'll take 5 minutes here to answer some questions. If you have any, if you don't, again, you can always contact our support group at support@adaptsoft.com. The video will be placed on our YouTube channel, youtube.com/adaptsupport, under the Adapt Webinars playlist. And I appreciate everyone's attendance today. Next week, we'll be having another webinar that it covers the design of beams within the program. So there is a question. Let me go ahead and open that. The question is, how do I get long-term deflections? The program, let me go ahead and open model here. Actually, this model will work. So in the input under the material, the concrete material, there's a creep factor. This is not a time-dependent program. We do have a program that does time dependency and sequential analysis, which is Adapt ABI. You could use it for these types of beams, but this is, we have to just assume some creep factor that the program applies. So when the program sees this input, the program automatically applies the long-term effect, or the long-term factor, this 2, to the sustained load. That's the self-weight, the dead load, and the post-tensioning plus some portion of the live load. So when you check the deflections, either in tabular format or in graphical format, those deflections inherently account for the long-term multiplier here. That's the short answer. That we do have more information in terms of a write-up. If you're interested in us sending that to you, we'd be happy to do that. Yeah, the webinar was scheduled for 1 hour from 2 to 3. We schedule it for a given time period, but the question is, why is the webinar not 1 hour? We schedule it for an hour, but knowing the content, we have covered that content. So that's again, if you'd like me to go for an hour, I can cover other topics, but we've covered the features in the program. The next question, in parking garages, is there a provision for progressive collapse against deteriorated tendons? No, I mean we don't have any input in the program relative to the deterioration, or let's say the loss of strength for a tendon. The user could always adjust the effective force or adjust tendon parameters to account for that, but it would have to happen in multiple models that each one maybe considers the effect over some period of time at some station along that time period. Question, please explain the output for stud rails for punching shear. And Chris, I'll answer that in just a sec. That'll take some more time to go through that in this model I have open. Let me just go to the next question. The question is, in Builder, is top steel considered in deflection, and how in a cantilever? The top steel is considered in a way such that when the program calculates the cracking moment of inertia, it's a function of let's say the cracking moment, it's a function of I crack, the crack moment of inertia, which takes into consideration the position and the location of the steel. So for each, we consider 5 load stages in the program, and the 5 stages that we consider for deflection, which are self-weight plus superimposed dead load, self-weight plus PT plus superimposed dead load, self-weight plus PT plus super dead plus live, and so on. We take 5 different calculations for each one of those stages. Each one of those stages is checked for cracking. So under each stage, we determine whether or not the system is cracked, and then we go ahead and we assemble the deflections with application of the creep multiplier to gather the deflections for the results. So yes, the question is rebar considered? It's considered in the calculation of the crack moment of inertia. Yeah, the question is, based on the title of the webinar, we are expecting to learn an introduction to using ADAPT PTRC. The webinar's purpose was to cover the features new to ADAPT PTRC 2017. So we apologize if that's not what you got, if that's not what you're expecting. Again, I would be happy to conduct a webinar with any of you who want a hands-on tutorial of how to use the software. We are doing one of those next week, on a week from today, which was also sent out to all clients. That will all be recorded and will be placed in the YouTube channel as well. Yeah, thanks. The question is, what is the allowable long-term deflection in a cantilever slab as per ADAPT? We don't, in ADAPT, we don't define allowable deflections. The program calculates the deflection. It takes the deflection divided by the span length to give you the L over span ratio, or the L over the span deflection ratio. It's up to the user to determine whether or not that meets code criteria. So in ADAPT, we calculate the deflection. The user should evaluate it for the code. The question is how much should I consider it as per ACI? That's not up to ADAPT. We don't instruct users on how to interpret the code. Maj, I would go and look at the code and determine what the code states. Okay, I'm going to go back up the list here. And Chris, I'll get back to your question on punching shear. There's also a question on curtailment. I'll cover that, Daniel. Just let me go get back into the program. I'm just covering what I can answer here without getting into the program. One-way slab with transverse beams. Just wanted to confirm that we should switch off the transverse beam option because the minimum reinforcement at the transverse beam 0.004 for the top mild reinforcement. So yes, if you're doing a transverse beam design, you likely would not use the total area of the transverse beam for the minimum reinforcement over the support. Okay, let's go back up to the questions that had more to do with the output and some of the input. So the question is, how should we interpret the output for stud rails for punching shear? And let's use, and then the other question was what is the curtailment module? What does it do? So I'll go ahead and cover the punching shear one first. If we run this model again, this is a two-way slab, and so we should get some punching shear reinforcement for this particular model. Okay, so we'll go ahead and exit out of this window. Now, in the input for punching shear for this model, and I'll use my marker here to highlight some things, but we said that there were 2 rails per side. So if we look at a column, let's take an interior column, for example, we're basically assuming that each side of the column, because it's an interior condition, that means it's a 4-sided critical section. Therefore, we would have 2 rails assumed per side. The user can modify this. I could say there's 2 on one side and 3 on the other side. So in this case, we have two on every side. So that's the first thing to understand is, number one, what is the categorization of the column? It's either an interior condition, which is 4-sided. It's either an end edge condition, which is 3-sided, or it's a corner condition, which is 2-sided. An end edge condition would look something like this, where you only have 6. If I enter 2 rails per side, I would have a total of 6 rails. A corner condition, if I have 2 rails per side, I would only have 4 rails. So we're going to look at this example up here with an interior condition. Now keep in mind that we are only checking the moment in one direction. So we're looking at a frame through one direction of the building. This column would likely be included in another frame in the transverse direction. So the user has to compile the results from each of those runs and determine which one controls in terms of the punching shear. Let me go ahead and erase that. And if I look at the summary sheet under envelope, I can see that for punching shear, column number, this is probably an end edge condition, so we'll go over here to support number 5. Number 5 requires reinforcement. Everything else is okay on the interior. There's 2 end edge conditions, left and right end, that are need reinforcement. This also requires reinforcement. So I'll go out of here. I know that I can go into my tabular reports, and I'm going to select punching shear reinforcement in my compact report. Okay, so in punching shear reinforcement report, we're looking at column number 5. It's condition 1, which is interior. Condition 2 is end edge condition, and condition 3 is corner. So for column number 5, down here in section 13.3, you can see that the program lists the column. It lists me the stud diameter that I assumed in the input, the number of rails per side in the B dimension, and the D dimension direction. And what it's telling me is what the distance is to each layer of studs from the face of the column. So for column number 5, what this does is I have a column here, and again I have, remember, 2 rails per side. So it's saying at a distance 1.6 inches from the face of the column, I need a stud on each one of my rails. At a distance 3.2 inches from the face of the column, I need another stud on each rail, and so on. This goes all the way out to 25.5 inches. So the last layer of studs is out here at 25.5 inches away from the face of the column. So I hope that covers it for you, Chris. The next question was, and let me go ahead and get up to that question here. The next question from Daniel was about rebar curtailment. So that's a great question. Honestly, I don't have a great gauge on how many people use the rebar curtailment option, but what it does is it bypasses the hard-coded way that the program arranges reinforcement. So this was introduced in version 2015. And in previous versions of the software, the curtailment was not there. There was no dialog menu for it. When you went and you calculated reinforcement, the way that the program output that reinforcement was purely based on this input here. So for minimum reinforcement, the program would say, take the top bars and cut them off at L/6 to either side of the support, or whatever the user defined here. For bottom bars, cut them off at 0.33. And the program had some very hard set rules on how we output the rebar in the summary sheet. So if the user wanted to customize the reinforcement, there's a way to bypass this, and that's the curtailment option. So in the curtailment schedule, for top bars and bottom bars, you have the ability to tell the program exactly how to cut off the bars, how far to extend the bars, what percentage of the total area of steel required for strength you want to consider long bars, and you want to consider short bars. So this is in tune with, let's say, ACI 13 section 13, where you can set up the way you wish to detail the reinforcement, both for top bars and for bottom bars as a fraction of the span length, for cantilever interior and exterior spans, and also how much reinforcement you want to allocate to the long bars versus the short bars. And there's also, you can use ADAPT's preloaded configuration. And if you study this, you'll find that this preloaded configuration really is just the same as this right here. You can user define this, so the user can set up whatever parameters you want in how the program will generate the rebar. There's also ACI preloaded default, Eurocode preloaded default, and then there's a few other settings here that allow and apply different options for switching on and off the rules. So if you wanted to apply it to only top bars, you could turn off bottom bar, you could turn off extensions of top bars over support, and so on. There's different things here that you can do to customize that. And then you can save these curtailment rules for other individuals if they wanted to launch the same curtailment file within their version of the program on their desktop, they could go ahead and open a file that you might save somewhere on a network, and they can bring in those curtailment settings. And those curtailment rules are reflective in the builder summary sheet when you output the rebar, both in builder summary and also in the block 10, so the reinforcement output. And there are ways to actually make changes to reinforcement when you're in builder summary. I'll show that here in a moment. Okay, so I'm just getting a solution here, and I'll exit out of Recycler. And then I'll go into the summary sheet right here. Now, let's say that you look at this rebar in the summary and you want to make changes to the rebar. Under options, you can go into reinforcement curtailment. You can modify the curtailment here, and then you can apply, and it would update the summary sheet. So you can actually update the summary sheet by accessing that curtailment through Builder Sum. There's also this option for reinforcement schedule, where you can dump all of this rebar into a scheduled format in an Excel file or a tabular file shown here. So you can copy and paste that into Excel or do what you need to do with it for purposes of scheduling the reinforcement. So those are a couple of things that some users don't know about that are available. Let me go over again to the questions. When we study, it says, by the way, when study are used, some columns need punching shear but not exceeding code. When changed to stirrups, it's giving exceeds code. So, Madge, there's different requirements that apply to stirrups and punching shear. For punching shear, you get a higher exceedance, 8 square root of f prime c versus versus stirrups, which the higher value, the maximum value is 6 square root of f prime c. So I recommend looking at the code in section, I guess it's section 11 of older versions. Section in 2014 is, I believe, 21. I'm not certain though. So there's just a higher allowable, maximum allowable for punching shear when you use studs. The next question is, when calculating the min and max peel ray in a beam section, does the program use the tributary width or the calculated effective width of the beam? The program always uses, and this is important, when the program calculates the pre-compression, it always uses the tributary width that is entered in span geometry. So in span geometry, if you enter the full tributary, it's based on full tributary. Even if you've selected to have the program calculate effective width, the pre-compression is based on full tributary. Everything else is based on effective properties. So the main frame analysis is based on effective properties. The flexural stress is based on effective properties, but the pre-compression is based on full tributary. Some users want everything to be based on effective width. So in that case, our recommendation is to enter the effective width as your main span geometry, and then make sure you increase the loading and scale the loading back up such that you're loading the full tributary. And when you do that, the program bases everything on effective width. The next question is, yeah, Chris, you mentioned, let me jump to this. In the example, the stud spacing was 1.6 inches. This seems too close. The slab, I don't know what thickness it was. I think it was 8 inches. I mean, I can look into the details of it further and we can verify that it's correct, but I don't know the details of the actual example. But let's take a look here. So it's an 8-inch thick slab. And if you want, I can send you a working hand example of the results to show that the program is correctly calculating the spacing for the studs. Next question. I'll go back to the pore strip question, Matthew. Is there some literature by ADAPT PT on how secondary effects are accounted for in the design, especially for concrete moment frames? We do have some generalized technical notes on secondary effects for the purpose of evaluating strength or factored loads. Matthew, if you send the question to support at adaptsoft.com, we will send you the technical note. Please do that, and we'll be happy to send you the technical note. Next question: what is the maximum length of tendon with single live end? With a single live end, Madge, again, please submit the question to support at AdaptSoft. We'll send you technical notes, but it's roughly 120 to 150 feet. We have a few recommendations in some technical notes. Sam, you say the screen is frozen. I can't tell on my end, but I'm not really working in the model right now. I'm just going through the questions. So the last question we'll entertain today is a question on the pore strip. So this is from Matthew. It says, for the pore strip example, you show the tendon live ends at the pore strips, not at the centroid. Does it create eccentric moments at the ends of the pore strip? Yeah, it would create eccentric moments if you follow the shape. But you'll notice under the tendon profile input, whenever for tendon C and for tendon B, if you select anchor at centroid, the program automatically considers the tendon end at the centroid. Therefore, you don't induce the moment due to the eccentricity. If you follow the shape, the second option, then if the shape falls at a location such that it's away from the CG of the member, then you would induce the moment. So this automatically locks the centroid or the CG of the cable at the centroid of the slab. It just forces the centroid to that location. Okay, I appreciate everyone's attendance. Again, this will be recorded and placed on our website. If you have any questions, any follow-up questions, please contact us again at support@adaptsoft.com. Thank you.